Hello everyone, my name is Mohak Goel. Today I will present joint work with Ashish Goel and Kamesh Munagala. In this work we study the matrix distortion of voting in the case where voters submit their preferences after deliberating in small groups. So the classical social choice problem is where each voter outputs a ranking over all the alternatives, and a social choice rule aggregates these rankings into a winner. So in this example, we have three voters and three alternatives. And if we were picking the winner by the number of top votes, that is the plurality rule, then in this case, we will have that A wins the election. However, there is a problem of information in the voting problem, and that is that the rankings do not capture the strength of preferences. For example, if a voter ranks A higher than B, then we don't know whether they like A much more than B or are they roughly indifferent. For example, in the same problem in the previous slide, let us say that all the voters who prefer A over B are roughly indifferent, whereas the one voter who votes B over A has a strong preference. Then, for the objective of maximizing the social welfare, the right choice would be to pick B as the winner. However, as we saw, plurality will pick A as the winner. In fact, no social choice rule which only uses the ordinal preferences can always find the social optimum. Therefore, in this line of work, we work with approximation ratios. And we assume that the voters have hidden cardinal preferences, which can be either utilities or costs, over the candidates. And we measure the performance of our algorithm or of our social choice rule with respect to the amount of sum of utilities or cost that it achieves in comparison to an omniscient algorithm which has access to the entire cardinal preferences. If we consider general utilities, then this competitive ratio is large. However, if we assume that the voters and the candidates are embedded in a metric space and that the distances give the metric cost between a voter and a candidate, then constant factor ratios are possible. See, here is a small example. Let us say if we have two voters and two candidates, and one voter prefers A over B and the other prefers B over A. The algorithm has to choose a winner by looking at these rankings, and let us say that they pick B. Now the adversary can pick a metric which is consistent with these rankings. However, the task of the adversary is to make the choice of the algorithm look as bad as possible. So this is what they do. They will put the voter who prefers B at a roughly equidistant point between A and B, such that their cost from B is only 1 minus epsilon and that from A is 1 plus epsilon, whereas the voter who prefers A has a strong preference and their distance from A is 0, whereas the distance from B is 2. So in this case, the algorithm which picks B has an approximation of factor of 3. We can also randomize our choice, and let us say if we picked our winner between A and B with equal probability, then in expectation we would have had the total cost of the algorithm be 2. So this is how we define metric distortion. A social choice rule is a function which maps any given collection of rankings to a possibly randomized winning alternative, and the matrix distortion is the supremum over all the matrix spaces consistent with the ranking, the worst case over all such rankings, of the ratio that the algorithm's winner has over the socially optimum candidate. So this is how some common voting rules perform on the matrix distortion framework. So couplet is a voting rule which considers pairwise comparisons, and the winner is the candidate which has the highest number of pairwise victories, and couplet has a distortion of 5. Random dictator picks a voter at random, and the winner is the top choice of that voter. And this procedure, which is very simple and has only one query to make from the entire population, has a distortion of 3. Whereas a very natural voting rule plurality in which every voter is asked for their favorite choice and the candidate which gets the highest number of votes is the winner, and the distortion of plurality can increase with the number of candidates, and it is in fact 2m minus 1. In fact, we know from previous work that if a voting rule is deterministic, then it can never do better than 3. That is, a deterministic voting rule can never beat a simple randomized voting rule as a random dictator. So in this work, we assume a different way of polling the voters, and we have that voters can deliberate over the alternatives in small groups, and in these small groups they can share their actual distances and their actual strength of preferences, and then as a group they can submit they can submit a joint ranking. So several online platforms facilitate this sort of a procedure where a random set of people can come together and discuss topics of societal interest. So this is our model more concretely, that if a group of voters meet and deliberate, then they will take the sum of the distances for each candidate, and then they will submit the rankings which are consistent with the sum of these distances from the entire group of voters. So this is some prior work on the distortion of deliberation. If the small groups can only return the winner or the favorite candidate after a deliberation, then from previous work we know that the distortion is at least 3. And here is a simple example. Let us say that we have deliberation on groups of 2 voters. Then when any group of 2 voters meet, they will pick the nearest black dot as their favorite candidate, whereas the socially optimum candidate is this red dot which is in the center of all of the 3 voters. However, if we are asking the voters for only their top choice, then we will only get to observe these black dots in the votes, and therefore we will never get close to choosing the red dot which is the optimum candidate. However, we also know that if we pick big enough groups for deliberation, that is, if the group size is logarithmic in the number of alternatives, then the distortion can go to 1. However, there is a problem with large group sizes, that is, it is seen from social science research that in large group sizes people become less candid and the conversation quality erodes, and people tend to avoid tough topics, and they also end up forming small groups within the large group, and this sort of coalition formation hinders the true revelation of people's preferences over the candidates. So the question that we ask in this work is, can we achieve a distortion less than 3 with constant group sizes? So in this work we will use tournament rules. We will create a tournament graph over all the alternatives, and for every pair of alternatives we will place an arrow from A to B if more than 50% of the groups rank A over B. And then finally we will use the Copeland rule to output the alternative with maximum out degree in the tournament graph. And here's a snapshot of our main results. If we aggregate the preferences over all groups of 2 agents, then Copeland's distortion already improves from 5, it goes down to 4.42. However, any social choice rule cannot beat 2.41. However, if we have groups of size 3, then Copeland can itself beat the deterministic lower bound of 3. It gets 2.81, whereas we also have a lower bound of 1.66. For general group sizes, we have that the distortion is going to be 1 plus order 1 over k. So here's the main technical idea. So if we are considering an election, if we are considering only pairwise comparisons, then it is enough to study the case where we have only two alternatives, and then we can use this result on two alternatives to then construct comparisons across the entire tournament graph. So for this case, let us consider that we have a bad candidate at -1 and a good candidate at +1, and the voters are distributed in the interval between -1 and 1. Again, we show that the worst case instances will only be there where the voters are between -1 and 1, and they will also lie on this line. So for the case of two alternatives, we show that it is enough to just consider this one line, and that too truncated between -1 and 1. Then we need to consider this quantity theta k, which is the following. So we have to find a distribution x supported on -1 to 1, which represents the distribution of the voters on this line, and then we take k samples from this distribution and let z be the average of these k samples. Theta k is the maximum possible mean of this distribution, which is a measure of how much the candidate at 1 is better than the candidate at -1 on average. And the adversary's task is to make the bad candidate win. So this is what they want to do, that they want to set the probability of the sum of these k samples being less than 0 to be at least half. Remember, when we discussed the tournament graph, we said that A beats B if the number of voters who vote A over B is at least half. So that's why we have this cutoff of half. So this translates into the technical condition that a median of Z is less than or equal to 0. Then once we obtain a theta k, then this is how we can obtain bounds on the distortion. The social cost of B is 1 plus theta k by 2, and the social cost of G, which is the good candidate, is 1 minus theta k over 2. And just by how we have set up the problem, we get a direct lower bound that no deterministic voting rule can obtain a distortion of less than 1 plus theta k over 1 minus theta k. So this is because the distances are not visible in the votes, and the bad candidate gets more votes than the good candidate. Therefore, no deterministic voting rule can do better than this quantity. For Copeland, we use the fact that any Copeland winner will have a directed path of at most length 2 to the socially optimum candidate. So we can take this ratio for each hop in the tournament graph and take the square of that quantity to give an upper bound for Copeland. So as a initial warm-up, we can consider the case of k is equals to 1, which is where there is no deliberation and voters vote individually. In this case, we can choose the distribution to be uniform on 0 and 1. That is, half of the voters are at 0 and the other half are at 1. In this case, the mean is half, and that is theta 1 is half. And we can see that the probability that Z, or just X in this case, being less than or equal to 0 is exactly half. So this constraint is satisfied. So this gives us a lower bound for deterministic rules without deliberation equals to 3, which matches the previous known results. And it also gives an upper bound for Copeland, which is 9, which is worse than the best known upper bound, which is 5, but this is a loose analysis. So things get more interesting for the case of two voters deliberating. So in this case, we have a pi-page rounding argument to show that the optimal distribution has support only on 3 points, which is -1, 0 and 1. And the idea is that if there is probability mass on 2 points -a and a, and if there is more mass at a than -a, then we can move both of these masses outwards, and by doing so we will only increase the expected value of the distribution, and we will also keep that the constraints are still satisfied if they were satisfied before. In the other case, that if there is more mass at minus a than at a, then we move both of these masses inwards, and by doing so again we only increase the expected value of the distribution, and again you can show that we do not violate the constraint satisfaction by doing so. So this shows that the optimal distribution will have support on at most 3 values, and then that makes our problem somewhat easier. We can define the probability of x being minus 1 as p, the probability of x being 0 as q, and the probability of x being at 1 as 1 minus p1 as q, and then we can write this optimization problem in terms of p and q. So in this case we get a linear objective function. However, the constraints are non-convex, therefore we need a non-convex solver. Fortunately, modern day solvers can solve this problem quickly, and we obtain that theta 2 is equals to square root 2 minus 1. Now this gives us a deterministic lower bound of 2.414, and an upper bound of Copeland can be achieved by a slightly different optimization problem which has more variables and a slightly more complex formulation, and we can get a upper bound for Copeland of 4.414. One important question that we have from this analysis is that can we design a voting rule which can beat 3 with only 2 voters deliberate? The case of 3 voters is slightly more complicated, and we formulate a more complicated non-convex program, and the state-of-the-art solver is only able to find this interval in which theta 3 will lie, and that is 0.25 to 0.2522, and this gives us a lower bound of 1.66 for any deterministic rule which takes the preferences aggregated over groups of 3, and at this point we get an upper bound of 2.81 for Copeland. For the case of general K, that is when we have a larger number of voters deliberating and submitting their preferences, we have the following result. As a lower bound, we can give a construction where the probability mass is on only 2 points. That is, there are the half of the mass of the voters is at x is equal to 1, and the other half of the mass is at minus 1 plus 2 over k plus 1. And in this case, we can see that the expected value of x is 1 over k plus 1, which gives a distortion lower bound of 1 plus order 1 over k. We also are able to get a matching upper bound by using the variation inequality, and we show that we can bound the difference between the mean and median of these random variables with bounded third moment, and that gives us a upper bound on the distortion of Copeland, which is order 1 plus order 1 over k. So in this paper we also consider a randomized model of deliberation in which for each pairwise comparison the groups will output a candidate with probability proportional to the total strength of the support in its favor. And in this case we show that Copeland can beat the randomized distortion lower bound with groups of size 3. So we have some interesting problems which are open from this work, and the first problem is, can we find an optimal rule for the case where only 2 voters deliberate? Another important question is, can we incorporate the case where the opinions or the positions of the voters actually change after deliberation? So in this case we will have to calculate the distortion on the new positions of the voters. And another question is, can we have a more realistic model of deliberation? And there are many practical questions which need to be answered when something like this is implemented in practice. That is, how do we sample the group for a deliberation, and how do we control for the fact that different people may have different persuasion abilities in the group? So people may misrepresent their strength of preferences to persuade the group to vote in their favor. So if do we need to add a layer of bargaining as a model of deliberation? And there are many fantastic questions here. Thank you so much for your time, and feel free to send me an email if you have any questions. Thank you.